This is your online module, Probability Basics. At the end of this module, you will be able to describe what is probability, differentiate between theoretical and experimental probability, and identify mutually exclusive, complementary, intersecting, and union events. Any process that involves variability can be modeled as a random process, which generates data. And that data is basically recorded from the outcomes of that random process. For example, let's say that we have the random process of tossing a coin. First, we need to explore what is the space of all possible outcomes. Like in this case, we have two options only, heads or tails. And the data that we collect basically will be the results of multiple trials of that random process. Like flipping a coin one time, then we get heads, flipping a coin second time, we get tails, the third time we get tails, and so on. The probability of an outcome is the proportion of times that outcome will occur if we observe the random process an infinite number of times, in theory. But in practical life, we cannot observe a random process an infinite number of times. Therefore, how can we have a shortcut? So, in short, then probability become the chance that an event of interest will occur, and it will have a value between 0 and 1 because it's calculated by the number of outcomes with the event of interest over all possible outcomes. Of course, the closer to 0 that this value is, the less likely that the event will occur, and the closer to 1, then the most likely that it will occur. Going back to a random process of tossing a coin, then if we focus on the probability of getting heads, there is one event of interest, which is heads, over the two possible outcomes. This is the theoretical probability. If we focus on the random process of throwing the dice, and we focus on the event of getting a 1, then the probability of getting a 1 will be 1 over 6, which are the possibilities. And if we focus instead on getting an even number from that dice, we know that the possibilities are getting 2, 4, or 6, making 3 over 6, or 1/2. So at this point, we need to differentiate really clearly between theoretical and experimental probabilities. The theoretical probability is basically what we expect, the expected probability of an event to occur, just like the ones that we showed in the example before, being calculated by the number of outcomes with the event of interest over all possible outcomes. On the other hand, empirical probability is actually the observed probability after conducting a number of trials. This is also known as relative frequency, and it makes the relative frequency of an event is the number of times that the event of interest actually happened and over the number of trials conducted. So in an example here, let's keep tossing a coin. So if we have 20 tosses, in theory, we expect that probability of heads is still 1/2. But if we actually perform the experiment of tossing 20 times that coin, we'll find that the relative frequency of heads will be different than 1/2. Like in this case, we have 12 observations for heads over 20 makes 0.60. However, that doesn't mean that the experiment or the trials are weird or have something wrong with them. It is just the fact that the more trials we get, then the closer I will get to the theoretical. This is known as the law of large numbers. The larger the number of experiments conducted, the closer these two probabilities will get. This is an example derived from throwing a dice. In this probability, in this plot, the probability of getting a 6th is plotted. Then the probability actually spikes at the very beginning, and then as the throwing keeps happening, then it actually approximates the theoretical one, which is 1/6. You are welcome to do the complementary activity on the link that I provide with this video, and roll the dice in a simulator by yourself and see how that probability converges eventually. We have another example here. Let's say that you have 12 cards that are numbered from 1 to 12 without repetition, and then one card is drawn at a time, and the number is recorded, and place the card back. We do this 50 times, and these are the results that we got. So in theory, the probability of choosing a 12 is 1/12, because they don't, the results are totally independent. And on the other hand, the relative frequency will require you to count how many 12s you have in the actual results and see how many of those over 50 is the relative frequency, which is 12%. So you see there are still there's still disparity between these two probabilities, but if we keep drawing a card, then these will eventually get to each other. So histograms can also be used to calculate experimental probabilities. For example, let's say that we got this data set for measuring the height of passengers, and we are interested on checking what is the relative probability of having passengers taller than 79 inches. So because of the division of my bins in the histogram, then we know that these two final bars will make for those passengers. Therefore, counting their observations makes the relative frequency of that to be 0.06. If we want to jump into the theoretical one, then it will be important to know the distribution of the data. For example, in this case, we can say that this is more or less modeled as a normal distribution. And once we have that as a normally distributed variable with characteristics mu and sigma, which are their mean and standard deviation, then we can calculate theoretical probabilities from those characteristics. So moving forward with some useful definitions that will help you throughout the semester are when you have more than one event of interests when calculating probabilities. So for example, let's say that you have a universe of possible events, and this is basically you have a probability of 1. I mean, like, you have the probability that something will happen or nothing will happen, but this is the space where that could happen. So this is the space that sums up everything to 1. Then I put a first event of interest, which is a bubble with the name A, and a second event of interest, which is a bubble with the name B. And I could put as many bubbles as I want, depending on the number of events, and the rules will be more or less the same. And the notation that is important for you to remember is that this U means union. This inverted U is an intersection, and the lowercase c is subindex c is the complement of event of interest A. So the first characteristic that you need to be aware of is independency of events. If two events are independent, then the probability of one doesn't change the probability of the other to happen. Okay, so for example, again, tossing coins, if we have two of them and they are identical, observing heads in the first one does not affect the probability of observing heads in the second one. So moving forward with the definitions, when we talk about mutually exclusive events, it means that when one event occurs, the other cannot occur. And the probability of the union for that will be just the sum of their probabilities. Examples, tossing a coin will be either heads or tails. They cannot happen at the same time, so they are mutually exclusive. And in this case, they actually sum up for the universe of possibilities. Complementary events actually is defined as the event that is not contained in the event A and is written by A subindex C. And you can see, like, if you have the whole universe, then anything that is not contained in that particular event is the complement, which basically facilitates your calculations, because if you say, okay, it's the complement, then the probability of that complement will be just 1 minus the probability of that event of interest. Then intersecting events. The intersection is basically all the sample points that are in both events simultaneously, like this gray area here, and is denoted by that inverted U. And if they are independent, the probability of that intersection is actually the product of those two probabilities. Like, for example, if we have that the event A is that I get an even number from rolling a dice, is my possibilities are 2, 4, and 6. And if I have event B, that is all numbers multiples of 3, which is 3 and 6, then the intersection of those two groups is 6 only. And finally, union events. Union events represent the event of containing all the sample points that are in either one or the other or both. So as you can imagine, if you actually just count A and B, then you will be double counting for the intersection that it's in both spaces. Therefore, when you are calculating the probability of the union of these two, you will need to deduct the probability of that intersection one time. Like in this case, for example, if we get the same events A and B, the union of the two would be 2, 3, 4, and 6. A quality control example to put all these concepts into practice. So let's say that a company in their products must pass 2 tests of quality control: materials strength and cycles to failure. And let's suppose that there is 15% fail the materials strength test and 12% fail the cycles to failure test. Both 5% fail both tests. So if we select a product at random, what is the probability that the product selected failed at least one of the tests? So stated in terms of events, then let's say that A is failing the material strength test and B is failing the cycles to failure test. So we have that the probability of A is 0.15, probability of B is 0.12, and probability of the intersection of them is 0.05. Therefore, calculating the union, which is how we translate having at least one of the tests failed, we do this subtraction of the intersection, and we get a calculation that 22% probability of failing at least one of the tests. So it's your time to practice. This is a reminder of the learning objectives. Check your understanding through taking the quiz.